Thanks for looking. So it's a pleasure to have Aline committees. So just a few words about Aline. She did her undergrad studies in São Carlos, then master's in Rio, PhD at Rutgers University, and now she's a postdoc at ETH Zurich. She's one of the candidates for the Fabesby-Simons tenure track position. And she's going to give a talking about large N, as you can see, from a theoretical tool to the left.
Okay, thanks Rogério for the introduction. It's really a pleasure to be here. I remember that I visited the institute when I was a student in São Carlos for the schools, so it's nice to be here giving a talk a few years later. I'm currently a junior fellow at the Institute for Theoretical Studies. This is a new institute at ETH, which is founded with some private money as well, and we have junior fellow positions every year, so if you're close to graduation, that might be something that you want to look at to be nominated for this position. It's a wonderful place to be. It doesn't matter if you're doing condensed matter as me or high energy physics, all fields there are also doing very well. So today, as you can see, I'm talking about large N. And I decided to talk about that because that allows me to connect a couple of things I've been recently thinking about. And as my audience is very diverse here, I will start making some parallels because many of you might be familiar with this concept within the context of quantum chromodynamics. But the aim here is to show that there are also counterparts in the condensed matter theory world. And I will start with this slide that makes a bit more explicit parallels here. So if you're familiar with the left side, I would ask you to try to keep in mind these parallels throughout the talk. So we all know that from quantum chromodynamics, we have the strong nuclear force, which keeps the quarks bounded, for example, in baryons, such as the nucleon, or the proton inside, the neutron or the nucleon inside the nuclei of the atoms. And there are three color charges with an associated SU3 symmetry. One can perform some renormalization group schemes and see that at high energies, these quarks are deconfined, meaning that the attractive interaction between them is very small. But at low energies, this attraction gets much stronger, and then we have the idea of quark confinement. And one way to theoretically approach these problems in the strong coupling limit is to use large N approaches, where we generalize the underlying symmetry group of the problem from SU3 to a larger group, usually taking to be SUN. And then we use 1 over N as a small, artificial small parameter to make an expansion. And on the right side here, it's the things I'm familiar with. We're dealing with electronic properties of materials usually, and then we are interested in electrons. These guys are charged, so the interactions are usually stemming from the Coulomb interaction, and this can be very strong, in particular in one class of materials called heavy Fermi systems. And again, electrons have spin with an associated underlying SU2 symmetry, and given the strong Coulomb repulsion, the electrons can effectively lose their charge degrees of freedom inside the materials and behave purely as spins. And that's what we call the local moment formation. And one can perform some renormalization group scheme analysis of the effective models we find here and find what is called the Kondo effect, which is the counterpart of quark confinement in QCD. And again, in this context, we have a strong coupled theory. Large N approaches come to be handy. And in this case, I propose that the generalization that we need to make is slightly different. It's not from SU2 to SUN, but to SPN, where SPN is the symplectic group. And that's intrinsically related to the fact that spins are objects that invert under time reversal. And I would like to finish asking a question: are these models with enlarged symmetries just a theoretical spherical Hall model, or is there any room in reality for these things to be realized in a laboratory, for example? And then in the end of the talk, I'll show you that that it's possible to realize both SUN and Spn symmetry in cold atomic systems. So as you might have noticed already, this is actually the outline of my talk. So talking about materials, I cannot skip this slide. We're talking about a bunch of atoms together in a given crystalline structure. And the periodic table as we know it organizes the elements, for example, in order of atomic mass as you go down, and each table by electronic similarity. What are the properties of the outer shell of these atoms, which are usually the most important things once you start modeling materials. And the elements I would like to focus on in particular are these guys, or highlight, which are the lanthanides, actinides, and some of the transition metals, because they have the most localized orbitals, 4f, 5f, and 3d orbitals. And to give a better sense of what I mean by localized, I will reorganize these lines of the periodic table as so in what is known as the Smith-Kmetko diagram. And here we have increasing localization as you go to the right and to the top in this table. So in this bottom left corner here, we have the most delocalized electrons. So once I put these atoms in a material, they will be in a lattice, some periodic structure. But given that they are very delocalized, their wave function with their neighbors will overlap substantially. And then we have something that looks very much like a metal. And that's well described by what is known as the Fermi liquid theory. On the opposite extreme, we have orbitals which are very localized. So when I put them in a lattice structure, the orbitals will have very little overlap, and I will mention to you in a second how that will lead to local moment formation. And this, the presence of this kind of atoms on this edge here usually indicate that we have some interesting magnetic properties. So the more localized the orbital, the more interacting it will be, because then it will be more energetically costly to put two electrons with a spin up and a spin down in the same atomic orbital. And that, as a consequence, will generate stronger correlations in the materials. Now, I would like to highlight three elements in particular, cerium, iron, and copper here, because they are the main drivers of the exotic physics we find in what is known as the strongly correlated materials. Exactly because they are in this intermediate regime between being localized and delocalized. So now I could go on and try to show you lots of interesting phase diagrams of materials that really exist. For example, these guys are heavy Fermion systems because they have cerium or ytterbium. This is an iron-based superconductor, this as well, and these are two different cuprate materials, which are high-temperature superconductors. So I won't go into any detail here, I just want to show that these things exist, and they have pretty involved phase diagrams. So I'll simplify that picture and show you this prototypical phase diagram with the main ingredients that repeat across this huge family of materials. And here we usually have a material which is antiferromagnet, and then we can tune the material. We can apply pressure, magnetic field, or we can dope it with some extra elements. And then we can explore this direction in the phase diagram, and usually that leads to the suppression of this magnetic order towards what is called a quantum critical point here. But usually above this quantum critical point, there is a superconducting dome. And more interestingly, above it, there is what is called a strange metallic phase, which doesn't behave as the Fermi liquid we know very well, but it has some very weird power law behaviors in thermodynamics and transport properties. And this is one of the things that we don't really have a good picture from a theoretical perspective, but it seems to be something quite universal that repeats in all this family of materials. So it should be related to some universal concept as well, and to properties of this quantum critical point. So the fact that we have these electrons in the brink of localization, it means that they are easily tunable between these two regimes of magnetism and Fermi liquid. And moreover, I am really interested in particular in heavy Fermion systems, because these are the ones we can tune by what I would call clean methods, meaning pressure or magnetic field, while these other families, such as the cuprates and the iron pnictides, I need to dope the material. So in some sense, I'm introducing at the same time some spurious effects due to inhomogeneities that I cannot control as well. So I'll focus on these because I believe they provide us with the cleanest set of evidences to try to characterize these materials theoretically. Yes, so that's what I just said.
Phase transitions among these different phases, they're all well understood?
Yes and no. Sometimes yes. For example, if you have an antiferromagnetic state out of a boring metal, some kind of spin density wave, then this critical point has very specific properties, and some materials behave very well like that, like cobalt. But once you go to these families of materials, when you have competing interactions, at the same time, you're not just suppressing this order, but you're creating some other order at the same time, then things are not as clear.
And the order parameter is usually what, magnetization?
Yes, here would be a staggered magnetization. Yes, and please feel free to interrupt me with questions if you have. So, okay, so then I'll move on to tell you about a little bit about how we model these heavy Fermi systems. And it goes as follows. So I told you that there is the main elements are these atoms with localized orbitals. And I'm representing here then in this square lattice, and each vertex of this lattice is one site, and I put one of these orbitals at each site. And the blue background represents the delocalized set of electrons coming from all other kinds of orbitals. That's already a non-trivial problem, so let me step one second back and show you the story for the one impurity problem. So now I have one impurity, one localized orbital embedded in this conduction C background. So we start usually with what is known the Anderson impurity model, where here we have operators in second quantized notation. The first term describes the dispersion of electrons with a momentum k and spin sigma for my delocalized background. EF is the atomic level of the impurity, which I denote with the F operators, which has the spin degree of freedom. This term tells me that there is some energy cost for double occupancy of these orbitals. If I have both up and down spins in this orbital, there is a U, a Hubbard U energy cost for that. And the last term describes a hybridization between this orbital and the conduction C background. So electrons can come in and out of this electronic level. So this is what I would say a high energy model, but I'm interested in the low energy physics of these materials. So to go in that direction and already imagining that I want to find a local moment at low energies, I'll ask you to look at this part of the Hamiltonian, which we call just the atomic part, independent of the background. So if I want a local moment as the ground state, I want the singly occupied state to be at lowest energies. So with that, all these both energies, U plus EF and minus EF, should be both positive. Now let's imagine now that I cool my material, I lower the energy, or lower the energy. If I lower the energy below, let's say, this higher lying state, I cannot thermally access it anymore. So then I have another, the respective effective model in terms of these X operators, which are Hubbard operators. We really project out of my Hilbert space things which are corresponding to double occupied states. I can go one step lower in temperature, where I cross the second level, and then what I'm left with is really just the spin degree of freedom. And the associated model at this energy, at lower energies, is what is known as the Kondo impurity model, where here I still have my conduction C background, but I have the second term, which is actually just a spin exchange interaction. It's just an interaction between the big S, which is the spin of this local moment, and little s, which is the spin density of this conduction C background at the impurity site. And this condo coupling, it's an effective coupling that came essentially because I'm looking at the fluctuations that I can do virtually here to this higher lying states. So you can imagine that from second order perturbation theory, that would look as v squared over u, because to go up, I need to add one electron from the background, let's say, to the impurity site, and then I need to go back, and the energy difference for that is u, so v squared over u. And that is positive, meaning that these spins would rather be anti-aligned, so we call this an anti-ferromagnetic coupling. And with this picture, we already, it's not, of course, the full story, but you can get a taste what I mean then by local moment formation, is that at lower energies, the spins don't have, at lower temperatures, they don't have enough energy to thermally access these higher lying states, so they are trapped and they just can access their spin degree of freedom. Now, I got this low energy effective model for my impurity system. Now, what if I want to keep renormalizing? What's the largest energy scale now that I can reduce and play with? So that's the energy scale coming from the electronic background. And we usually associate that with a band, so sets of states that occupy a range of energies between minus d to d, what we call the bandwidth. And now I can keep renormalizing because I can keep eliminating the states which are at the edges of this band systematically. And then I will do that calculation and see how that changes this condo coupling. So if I do that, what I'm effectively doing is computing diagrams that looks like this. Feynman diagrams, where the dotted lines correspond to the F electrons, and the blue lines correspond to the conduction C background. Now the dark ones in the intermediate states here are the states I'm integrating out at the edges at higher energies. So I can do that systematically, and I see that in terms of dimensionless quantity, Jk over d naught, where d naught is the bare bandwidth, this energy scale, I get a beta function which is in fact negative, meaning once I reduce the energy scales, my coupling gets even stronger and stronger. And within this second order calculation, one can identify a scale at which this coupling actually diverges. And that's what we call the condo temperature. So now looking at this picture, it means that at some temperature, meaning this condo temperature, the local moment, the spin from this F electron, will be forming a bound state with a spin coming from the conduction C. So that's essentially asymptotic freedom in a cryostat, because at higher energies, we see this spin completely free. And the hallmark of that is this Curie-like susceptibility we all learned from statistical mechanics. But at below this characteristic temperature, you really form a bound state. You cannot access, you cannot polarize this local moment anymore. Therefore, you have a flat susceptibility that looks just like a metal with no local moment. Now, this was the story for the single impurity. Now I need to go back to tell you a little bit more about the lattice. So in the lattice, we have the condo lattice model, in which case we have an associated quote-unquote impurity, or a local moment at each site, coupling to the conduction C spin density at the same site. So now instead of we still have this idea of condo temperature, which defines the energy scale below which I form these bound states. But now at the lattice, given the periodicity of this array of local moments, we have the development of what called the heavy Fermi liquid state, where these local moments are absorbed by this conduction C background, making them harder to move around. And then, as a consequence, the effective mass here, as the inverse of the second derivative of the dispersion, gets much, much higher, what can be 100 or 1,000 times the bare electron mass. Given that we are in the lattice, we have a second energy scale, what's called the RKKY temperature. And that's because now these local moments at different sites, they can talk to each other through the polarization of the conduction C background. So one local moment here will polarize the delocalized electrons, and as a consequence, this second local moment will field it. So this energy scale, you might imagine, is related to the density of states of this conduction electrons and times jk squared, again in some second order perturbation scheme. So now I have two energy scales to look at, and they have different functional dependence on this Kondo coupling. So if I would plot what is called the Doniak phase diagram as temperature in terms of this dimensionless quantity, density of states times jk, I find something that already qualitatively reminds me of the phase diagrams I showed you in the beginning, meaning at low jk times rho, I have that the RKKY temperature is higher than the Kondo temperature, meaning if I start lowering the temperature of my system, I will first hit a transition to a magnetic order. But if the parameter is large enough, the Kondo temperature is the highest. Therefore, as I lower the temperature, I form this heavy Fermi liquid state in which I kind of screen all these local moments in the lattice, and I don't have anything to form a magnetic order anymore. So this looks like the phase diagrams I showed you. So that's more or less how we understand how these things come together.
But it's not quantum phase transition in this case, right?
It would be a quantum phase transition if you're crossing here at 0 temperature.
Yes, but before you showed the phase diagrams in terms of magnetization, there are not quantum phase transitions.
Yes, so in what I showed you, I could tune the material, for example, by pressure or magnetic field, right? And in that case, of course, I cannot do the experiment at absolute 0 temperature, but I can do that at low enough temperatures that I know I can extrapolate it to 0 temperature. So I would call it a quantum critical point because we can have actually a lot of information from the thermodynamics at low temperatures about the properties of this point. So I would still call it a quantum critical point. Okay, so from this first part, I would like you to take home two messages. First, that there are these materials called heavy fermions, and the interactions inside them are usually very strong, and it's hard to model them, therefore. And that the effective models involve these objects which are kind of spins, pure spins, which we call local moments. Now, we find these effective theories with rather strong interactions. How do we deal with them? So you already know the story from quantum chromodynamics. We can enlarge the symmetry group of the problem from SU3 to SUN, take n to be very large, and then use 1/n as an expansion parameter. And that seems to be convenient because, for example, if I want to describe a baryon, I know it's a singlet bound state of 3 objects. Therefore, in the large n limit, I would have an analog singlet object, which would be an n-body bound state. And that seems to work quite well for quantum chromodynamics. But in condensed matter, perhaps we need to think a little bit more careful because of the nature of the singlet states we are interested. For example, if I'm interested in superconductivity, we have the formation of Cooper pairs, which is essentially the formation of a bound state between electrons with opposite momenta and spin. Therefore, I form a pair between states which are time reversal, the time reversal of each other. And also, if I'm interested in some exotic phases in magnetism, there is known, for example, what is known as a quantum spin liquid state. One way to describe them is in terms of valence bonds. So each of these ellipsoids in a triangular lattice represents a singlet between the neighbors. And then the state of the system is actually a superposition of all the different configurations of this, all these possible configurations of valence bonds. So in these two cases, we have intrinsically the idea of two-body singlets, two-body bound states. So perhaps, and the idea of time reversal symmetry also appears very clearly. So then the question is, in the large n limit, what are these bound states that I will form there? So if I require that the enlarged symmetry has some transformation u, and that this u will be in agreement with time reversal symmetry, meaning it will commute with time reversal symmetry, here denoted by theta. If I rewrite this condition using that time reversal is essentially a complex conjugation times an antisymmetric matrix, what I get is what is known as the symplectic condition, that antisymmetric measure is left invariant under this orthogonal transformation. So that suggests me that perhaps a more appropriate generalization for the large n limit in this case is from SU2 to SP and the symplectic group and not SUN. Now if I look at the generators of this group, if I take them, if I write this transformation by the exponentiation of the generators, what I get from this condition is the equivalent of saying that the generators of the group properly invert under time reversal. What is not true if I look at the family of generators of SUN. So if I work in this generalization, I can define objects in this large n limit which properly invert under time reversal. So there, I would say that are good generalized spins. Yes?
Sorry, can you repeat that for me? What is U again?
U is some transformation of my enlarged symmetry group. So I say that I have a unitary transformation that can be associated with, for example, SUN. That's the standard way to define it. Usually the antisymmetric measure comes from the fact that you have associated states in some bases which are time reversed of each other for that degree of freedom, right? Yes, so the fact that it's symplectic is a direct consequence of the fact that time reversal has this anti-Hermitian property of its own.
So the analog of color in your case is higher spin?
That's one way to say it, but it doesn't mean that it's just a large spin. It's not a larger representation of SU2. I have extra directions into which the spin can point to. I don't have just an object that goes to the classical limit that looks just a big spin, like a big spin, just due to products of SU2s.
And SP2 is some sense equivalent to SU2?
Yes, that's right. Sorry. Okay, so I motivated this scheme to use SPN instead of SUN. So now if I look at my Hamiltonian, what do I gain with this new scheme? So let's say, yes.
You also have time reversal invariance.
Yes, but that is what I'm referring here is to the properties of the objects, of the generators themselves. Because I want to find an object that in the large n limit will be well behaved under time reversal. Oh. Okay. Does that answer? Okay, so if I have this generic exchange Hamiltonian, now 1 and 2 are spins at, let's say, different sides or corresponding to different orbitals. It would all be falling in this case. Then what would be the S dot S, as we know, as Pauli matrices, as X, X, Y, S, Z, goes to this generalized Hamiltonian, where now I'm summing over all the generators of my underlying symmetry group. And these generalized spins I can write in terms of creation and annihilation operators, with the respective generators here, and you might be familiar with this, with the Pauli matrices here for as you choose spins, right? So if I plug this in, what I find is a four-body term like this with this, let's say, form factor, which is actually related to the completeness relation of the symmetry group. And that will be different if you're looking at SUN symmetry, which has this form, in which case you can simplify this Hamiltonian to something like this in terms of these A operators, which are bilinears in my fermions. And they look very much as hopping. So I'm destroying an electron in one site and creating it in another site, for example. Or if I'm thinking about orbitals, would be a hybridization term. Now, SPN, I have a different completeness relation that looks like this, and it brings into my theory a new possible decoupling in terms of this B operator bilinears that look like the things I want to find, because this is essentially a singlet. It's something, let's say, with spin up and down minus spin down up, where alpha here, alpha tilde, is the sign of alpha. So this scheme, if I construct a large N with this symmetry, naturally gives me a decoupling in this channel that looks like pairing, like superconductivity, or valence bonds that would allow me to describe exotic magnetism.
So the symmetry acts on the fermions?
No. So the symmetry here I'm referring to is how these underlying objects transform. So
it's not the symmetry of fundamental theory, the symmetry of the object?
yeah, so as a consequence of that, of course, this term will be SPN invariant if once I explicitly write the completeness relation as so.
So the group is acting what? It's hard to get, because I'm used to the CD part. So I know that SN acts on quarks.
Yes. So in this generalized spins, or in the generalized spins.
Okay, so for quarks, if you have a large SN means that you have a larger representation of n fundamental representation. So these objects are in fundamental representation?
They can. I didn't say in which they are, but yeah, here that would be the case, and then alpha and beta would be the indexes related to. Would run from, let's say, if I have SUN from which, okay, SUN would be 2F plus 1, 2S plus 1, where S would be the analogous of my spin, so it would run essentially from minus S to S. So, okay, maybe I can say it that way. So I'm constructing the goal is to construct a theory in terms of objects which are well defined in the large N limit concerning time reversal symmetry. So these objects are related to the generators of this underlying group. Therefore, as my interactions look like S dot S, as a consequence of that, my theory is SPN symmetric. Because I chose to deal with those, I'm constructing a theory out of those objects. Out of these objects. So that the trans are the fermions inside. Yes, it would be, I believe that would be the analogous of the quarks. At each site, you can transform that independently. In principle, yes. So then if you're in a lattice, you can construct some associated gauge theory for that. It can, but usually we focus on developing, let's say, well-controlled mean field theories for that. You can try to associate these bonds, give them some dynamics, some gauge field associated with them, and that's usually associated with some more exotic spin liquid states, but that I won't be talking about. Not necessarily. This could be already some effective model for some magnetic material. Let's say I already know that I have the local moments, and no, there are materials that have this as an effective model. That's it. All right. Yes, so yeah, so that is in principle a thing that is particular to these materials that have these local moments as the effective objects I'm dealing with. And if you remember, I had this tower of states in the beginning where I completely washed out the charge degree of freedom. So effectively, these guys are really spins. They cannot hop around. So and parity. Parity, I'm not sure how parity would come in here. It would probably be associated with the underlying symmetry of my lattice. So that would be embedded if I can construct, well, this was just for, let's say, 2 sites, but it can have the associated model with the underlying symmetry of the lattice I'm working with. And then if I write my effective models as so and propose this large N scheme, then I can go over the standard calculation of writing my path integral, making sure that my action is scaling all the terms to scale with n in the same way. I can decouple them by what is known as a Hubbard-Stoyanovich transformation. I can find a saddle point solution as a starting mean field solution, and then I can go ahead and evaluate also effects of fluctuations and so on. So if you're familiar with this, you know already the recipe, but if not, the bottom line of this part of the talk is really to motivate this kind of scheme that gives me more possibilities in the decoupling. So the take-home message from this part is that large N approaches are also useful in condensed matter theory, and that we sometimes require a different scheme for these calculations using different symmetries, not as UN, but as PN. Yes. Even in what kind of phases you're able to describe, for example. In SUN, I don't even have access to superconductivity in principle if I don't put it by hand. But in the SPN scheme, that is naturally there. Yeah, or at least give me the possibility to have an order parameter to that phase I'm interested in, what would not pop up in the SUN scheme. Okay, so then the question is, okay, I have these schemes, I can generalize my model to something else which has a larger symmetry, be it SUN or SPN, but then I can do my calculation. Are these just idealized models, spherical count models, or is there any degree of reality to this kind of models? So this is a good opportunity for me to show you a beautiful picture of Zurich. The main building is somewhere here, the old building, and I have an office. The Institute for Theoretical Studies is somewhere here. This is the other campus where physics and engineering and chemistry are mostly. This is the physics building where the theoretical physics is located here on the top. So in a nice day, we have quite nice view from the Alps. That's very sweet. And as you might see, there are lots of green around. And these are really pastures. So there are cows there. And you know, all the chocolate and everything. And it's not rare to find them actually eating right under the ETH sign. It's quite cute. Okay, so that's much about cows. Now, ultra-cold atoms. So I recently became interested also in this area because it provides us with a very flexible platform to simulate models that can reflect the physics or the effective physics inside materials very well, and even go beyond it, realizing models that we just came up with theoretically that don't have easily a parallel with material science. So the setups look more or less like this. It's a tabletop experiment, and they can realize essentially they can trap different kinds of isotopes in different geometries. They can trap it in 3D, or they can make a lattice, or they can make this lattice of one-dimensional arrays. They have a lot of flexibility. And for example, here you have these balls with different colors and some arrows. And the different colors are associated with different hyperfine spins. So if you remember, if I look at the atom as an object itself, due to hyperfine coupling, the electronic degrees of freedom are coupled to the nuclear spin. Therefore, I can have a hyperfine spin. The total spin of the atom can be up to, for example, 9/2 in strontium 87 or potassium 40. Now, this says ultra cold, and how cold is ultra cold is of the order of 10 to the minus 6 to the 10 to the minus 9 Kelvin. Sorry. So, just as a curiosity, things that I have been addressing in this talk from quantum chromodynamics, where the characteristic energy scale for the formation of the bound states is around 1 trillion Kelvin. We have also the Kondo effect, which happens usually around tens of Kelvin, and now ultra-cold atomic physics happens in the range of 10 to the minus 6, 10 to the minus 9 Kelvin. So we have 20 order of magnitudes in energy in a single talk, what I think is quite cool. And as a second fun fact, next year they are launching to the International Space Station ultra-cold atomic lab, which is supposed to achieve temperatures as low as a picokelvin, what would be the record ever reached. Fine, okay, but how do we model the systems? It's actually might be familiar to you, because we have a non-interacting part and an interacting part of this bunch of atoms, which are in principle trapped in a potential in space. So here I have the usual kinetic term, and here I have this external trapping potential. And the interacting term, what it does here, it allows for scattering of any kind of atom with any hyperfine spin component to anything else, given that I conserve total angular momentum, what is encoded here in the Hamiltonian by these Clebsch-Gordon coefficients. And here I already make evident that the magnitude of this scattering depends only on the total angular momentum of the pair of atoms which are scattering. Therefore, I label it as G of big F, where the little f is actually the hyperfine spin of each atom separately. So the non-interacting part is rather trivial and is rather symmetric under both SUN and SPN. So the presence of the symmetry will depend on the properties of these different G's on the interacting term itself. So SUN symmetry as you might imagine, tells me that I can rotate between all these colors, between all these hyperfine spin states, and fall back into the same Hamiltonian. And that is realized in alkaline earth atoms, which are in the second row of the periodic table, because the electronic degrees of freedom have a full field shell, meaning 0 angular momentum and 0 spin. And given the fact that the scattering between these atoms depend mostly on the electronic properties, in that case, the featureless electronic shell tells me that all the couplings are the same in all the channels. And then as a consequence, we have a very trivial vertex, which doesn't allow for anything interesting to happen. You just scatter from green and red to green and red. So consequence of that is that the number of particles in each color or in each hyperfine spin state is conserved. Now, for Spn symmetry, something different should happen. So Spn is a subgroup of SUN, so I would need to loosen up a little bit this constraint. And the condition for Spn is that the coupling in the 0 total angular momentum channel is different from all the other ones. And that is naturally satisfied for isotopes with hyperfine spin equals to 3/2, which don't fall under the alkaline earth atoms. And interestingly enough, now in SPN, more interesting things can happen, because on top of the original scattering, I have a second scattering channel. And here I took the freedom to write the states a bit different. I use both a color and an arrow, because now with the arrow I can associate time-reversed states, so the up and down. And then scattering now is allowed between these time-reversed pairs, and then you can have color transmutation. And a consequence of that is the fact that a color magnetization is preserved instead of the number of particles in each color. Yeah, it is not representative of anything in particular. Yeah, I could just have put a point. Oh, this is just a property of this interacting term. Yeah. No, yeah, it's just a symmetry of the Hamiltonian. So now I will go back to the periodic table, now in another context, because I'm interested in different isotopes. And the color now in the table represents the dipolar character. Dipole-dipole interaction is a rather long-range interaction, and I didn't tell you, but I assumed there that I have rather local interactions to have that effective interacting term. So I will rule out these guys from my search of elements to realize Spn symmetry. Another constraint I would like to impose is that I'm looking at stable elements. I really want to do that in the laboratory. So anything above lead is also ruled out. Now, I want something with an enlarged symmetry, so I would like something with a hyperfine spin which is larger than 1/2, and also that it's fermionic, and that rules out a lot of things. So we are left with these guys, which are in the darker blue. And if you remember, the alkaline earths are these guys, and this will realize as UN symmetry, as well as these guys, and ytterbium, because they all have a completely full electronic shell. Total angular momentum and spin are equal to 0. So what I'm left with are 3 isotopes. 1 isotope of potassium, 1 isotope of boron, and 1 isotope of germanium, which can generate respectively sp10, sp6, and sp8 symmetry. So it's rather frustrating that even though I'm searching for something that is less symmetric, Spn is a subgroup of SUN, I find less options to realize it. So nature somehow likes more symmetric things. So from this part, I would like you to take home the message that it is possible to realize in the laboratory something that has an enlarged symmetry, in particular SUN and SPN. And interestingly enough, SPN is less common than SUN symmetry. And to conclude, I'd like to give some perspectives of other things one can think in this direction. For example, if you put a bunch of fermions together, the first thing you want to do, even before thinking about any kind of order, is to characterize the Fermi liquid behavior. So because you have this different symmetry and different scattering channels, the Fermi liquid behavior will be different. So the effective quantities in the thermodynamics will scale differently with n compared to the SUN case. And in particular, this is the Wilson ratio as a function of n. This gives a measure of how close I am to a magnetic instability. So for SPN, we see that it's possible to have an enhancement towards magnetism. What is interesting if you're trying to do this in an experiment. One can also use the symmetries as a design scheme, since I showed you that you can find different decoupling terms if you use one symmetry or another. So this can be used as a design to find ground states with different orders. There are also interesting connections with physics and higher dimensions, that in two contexts. First, one can use a tower of states in each atom as another effective direction. One can use resonant fields that would take you from state to state, and you can rewrite your Hamiltonian in a smart way that it would look like an effective spatial dimension. In another context, there are interesting isomorphisms, in particular SP4 and SPn5, which tells us that perhaps if we are able to realize a system with SP4 symmetry, we can have access to fundamental physics in 5 dimensions. And furthermore, this can be more generally used as simulators for both quantum models that can describe materials, but also lattice gauge theories, as many of you might know, that can be effectively constructed in the laboratory. So instead of making computations, you can measure your correlations from observing a system in the lab. So with that, I'd like to conclude with this slide again, because we started with a concept from high energy physics, which found its way through condensed matter, but now atomic physics also came into play and provide a way to simulate physics in both directions. And with that, I would like to thank you for your attention.
Thank you, Aline. So we have time for questions.
So normally, if you want to do theoretically large n, you compute some property which is valid in the large n limit, and then maybe it would be interesting to see if n equals 3 for QCD would be large enough to be relevant for these properties. Is there something similar with these SPN? Is there some property you can predict and then check if the material has those properties?
Yeah, so in principle, the underlying electrons have an SU2 degree of freedom, so n is rather low. So the difficulty here is that when you talk about making direct connections with experiment, because the underlying microscopic theory with all the other delocalized degrees of freedom sometimes can play an important role. So the matter is, do I have a background and the interactions which are fair enough to describe that system, and then I can do my large n, and does that recover the phenomenology I find? So I'm more interested here in describing the phenomenology qualitative at this level, because we don't even have that systematically. How to marry all those phases I showed you in that generic phase diagram in the beginning, more than trying to match one critical temperature or one magnitude of the gap, because that's very hard and usually relies on some numerical studies. But I'm interested in providing the framework that allows me to marry all these phases together. But that doesn't answer your question, because you asked if I can compute some observable as a function of n.
Yeah, for large n.
Right. So then the question is, yes, how strong correlated is my system? Because I can compute something to first order, and I find that, I don't know, the power laws I get are not right. And then I can go one order higher and see how that corrects, if it changes effectively something that is very robust, which you see in thermodynamics or transport. So this could be matched more than magnitudes of specific things in materials. So I'm interested in more universal properties, such as power law behaviors around these transitions and so on. So that's the dream. That's what I,
Hi. Do you know if someone considered this generalization to SPN in the Heisenberg spin chain? I mean, I'm interested in integrability, the implications of this new group for integrability.
Yeah, there are some versions of it that were done in the past. If you look at the literature, actually there is something that they claim it's SPN, but it's actually not exactly what I showed you. The model is Spn symmetric, but the generators are, as they build it, are not well defined under time reversal. So that's some work in the 80s actually. And there are more recent works in the early 2010s that recovered this point. And there people were more interested in looking at frustrated magnetism, for example, and that you can find some Heisenberg-like models.
Yeah, some people from the QCD side, they are making calculations in the large N limit using this ADS QCD duality. Just you go to one dimension more, just including gravity, and then you have a perturbative theory. So is there anything similar here with SPN, what you said today?
Yeah, that's something I'm not a specialist on. I know that there are people studying things in that direction. Mostly, yeah, to try again to marry these phases or find interesting critical phenomena and so on. But yeah, I would not be able to go beyond the parallel I gave you in the talk. But it's an interesting direction.
More questions? Okay, so I don't see any more questions, so let's thank Aline again for the colloquium. And there should be some refreshments upstairs.